All right, class, today we're going to be studying section 4.3, graphing exponential functions. First, we have to consider what is an exponential function. An exponential function is not any number being raised to a power. An exponential function is a function in which the variable is in the power position. So an example would be f of x equals 2 to the x power, or f of x equals 1/3 of x, or even f of x equals e to the x power. This is a very common exponential function. The key thing is the variable is in the power position. In general, a graph that is not stretched or shifted will have an x-intercept at, a y-intercept at the point 0, 1. Because anything raised to the 0 power is always 1. When you're graphing exponential functions, in general, if they're not stretched or shifted, your graph is going to look something like this. And you're going to have a horizontal asymptote. This horizontal asymptote occurs because no matter what number you plug in for x, for example, 2 to the negative 100 power, notice it's very, very small, the number itself is going to become very, very small, but is never actually going to touch 0. So the horizontal asymptote is at the x-axis, or the line y equals 0. Just like when we graph any other function, we always want to focus on our important parent points, okay? We're going to plug in -1, 0, and 1 for x. Now our parent function could be a lot of different things. It could be y equals 2 to the x, y equals 1/2 to the x, or y equals e to the x. It doesn't matter what the parent function is, but you'll figure out your parent points by plugging in x equals -1, 0, and 1. The rules are the same as they would be for graphing any other function. The number being multiplied out front multiplies to the y. The number being added or subtracted on the end, that's your vertical shift, or your up or down, going the same as the sign. Then operations with x happen in the power. The base could be anything, and your base will help you determine your parent points. But anything occurring in the power, we always do the opposite, and it's going to affect how our x's change. So the a gets multiplied to the x's, and you're always going to do 1 over that. And then the minus b, that's your left and right shift, and you always go opposite of the sign. So let's do an example. First, we want to think about our parent function. So in this case, our parent function is the function of x equals 2 to the x power. So let's figure out our parent points. To find our parent points, we plug in -1, 0, and 1. So 2 to the -1 power would be 1/2. 2 to the 0 power is 1. And 2 to the 1 power is 2. So I'm going to plot my parent points just like I would any normal function. -1, 1/2. I have to approximate that. 0, 1, and 1, 2. And this graph is going to increase very rapidly. Notice, there is an asymptote here. We're going to get very, 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 very close to 0, but we're never actually going to touch it. Again, imagine if I plugged in -100 in for x of the parent function. I'm going to plot my asymptote because my asymptote might have to shift depending on the shifts that I have. So now that I figured out my parent functions, I'm looking for stretches, and I don't have any number being multiplied out front, and I don't have any number being multiplied in the x's, so it looks like I only have shifts. Every point in this graph is going to shift the opposite of 2, so backwards 2, or negative, or left 2, and then down 3. So whenever I have a vertical shift, my asymptote is going to shift as well. So my asymptote is going to shift down 3. So here's my new asymptote. And then every point is going to shift down 3 and to the left 2. Down 1, 2, 3, and to the left 1, 2. Down 1, 2, 3, and to the left 1, 2. So my final function is here. We'll continue more with graphing exponentials in class. Please write down any questions that you may have, and we'll cover them.